Hey there, Nines. So today this is going to be more of a guided notes lesson than anything else. So by the time we get to, I think, my fourth slide, you'll want to have the activity open along with the video, and we'll kind of like talk a bit in the video, and then you'll do some work, and then you'll play the video again, and we'll be going back and forth. So that said, I wanted to talk a little bit about some of the things that you saw yesterday. Yesterday, option B is an exponential function. And so today we're going to continue talking about exponential functions. I'd like you to know that in general, they look like this. And so we have y equals a times b to the x power. By order of operations, we have to evaluate b to the x power first, and then we would multiply by a. So in option B yesterday, you were looking at the starting amount was 1 penny. So A is that starting amount that we'll multiply. Your rate of growth was 2. Things were doubling every month. So since things are doubling, your rate of growth is 2. T is time in months, so we're doubling every month, and you would double for the number of months you have, and then multiply by the 1 penny that you started with, and you would get the amount that you have earned in euros overall. The important thing about exponential functions is that invested money grows exponentially. So today I want to transition with your understanding to the first stage of an investment function. Like we've just started looking at these type of functions. I really want to transition to looking at this type of function. And you can see that these functions do work similarly. Here we had A that we haven't dealt with much, but you can see when we look at option B yesterday, that A is a starting amount. So down here, we have this P in front, and it will function the exact same way that A does. That'll be a starting amount. We call that P principal. I should put there. P equals principal. Oh, with all caps, I'm shouting principal at you. P is principal. The principal that you invest is the initial amount that you invest. So after you've invested that amount, your money starts to grow here, and this is a little bit strange. So I want to back up and look at up here. We had this B is like the base on the exponent. Here you can see that base is the rate of growth. So when things were doubling, that rate of growth was 2. Well, this rate of growth seems a little bit different. It feels strange, and so I'll tell you why. Is because we say that money grows at things like whatever. If you get a really good investment, you invest and it's going fast, your investment rate would be 10%. So 10% as a decimal is 0.1. And if you multiply your money by 0.1, you lose a ton of money because you don't have 100% of what you started at. You only have the 10% that you gained. This is why we need to add 1 plus R, because R is the amount you're gaining, but 1 is the amount you have initially. So this is 1 plus R is basically saying, I can type this, 1 plus R is saying 100% of your investment plus R% of your investment. So just to give you an idea, that's why the investment rate in this function looks different than in this one, but it really works the same. This was saying you keep all the money you have and you get 100% more, hence you double. This one is saying you keep 100% of your investment, that's the 1, plus you add some amount, which is the amount that you're earning on an investment. And in real life, 10% is a really good rate of return. So that said, I wanted to look at some of the things yesterday. There are a few misconceptions that come up, and these are common. Like I expected this to happen. These misconceptions have the exact same effect in the end. So let's look at them. This one, when you look, is a little bit hard to follow, but you can see here, this is stage 10. So stage 9, 8, 7, 6, 5, 4, 3, 2, this is stage 1, like 1 month in. And that's totally fine because in option A, today on month 0, you get 0. So in month 1, you do have 6,000, and this student's table was correct for option A. But if I look at option B, down here they have 14, which tells me this is 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. This is month 1. The problem over here is that in month 1, you should have more money. Like in option B, in month 0, you got 1 penny. 0, 1. which means in month 1, you should have 2 pennies. This should be 0.02. This is a common misconception for students to do. And the real reason that it happens is that most students start at X value 1. But if we're considering time, we always need to start at month 0, always. Month 0 is today, really. So you have to start with thinking, what's happening today? That's your initial input. And then what happens as time goes on? So then we get month 1, 2, 3, 4. But don't forget month 0. It's super important. You can see in this example, since the student missed month 0, they doubled one less time, and the effect in the end is like 1,000 euros or something. It's a huge amount. So, okay. This other student had a similar thing, or a similar problem that had the same effect. They started on the 1st of January, which is fine. If we start today, it's obviously not the 1st of January, but they're starting on January and going forward. Well, great. But if January is month 0, then when I count out December 2 years later is month 23, which means this student needs one more month in order to hit that 24th month. Really, like January through to December is not 2 years. That's the problem. And it's the same issue. It's that this student, you can see it here, started on month 1 and went to month 24. Well, it's not month 1 today. Today is month 0. Don't forget month 0. So this student also has the issue where they need to double one more time here. They actually should get 6,000 more euros here, and then this table would be resolved. But when you set up a table and you are considering time in any form, it is important to know today is time 0. So good. In graphs, here were some graphs I wanted to talk about that I really like both of these graphs. This graph has all of the pieces that I asked for except for one, and I would say the one that this student left off is the least important of all the pieces I asked for. I should have pulled up your guys' assignment already. Do I have it here? No, I don't. This student definitely started at month 0. I don't like 0 in the corner here. I would rather have a 0 on the y-axis and a 0 on the x-axis, because this looks like the student thinks 0 is where he's starting, but this is not the point 0. That's the point 0, 0. And it's important that we have an x coordinate of 0 and a y coordinate of 0. That is massively important. So that would be one gripe I have. But they labeled their axis, labeled their y-axis also. They told me the interval that they're counting by, and the interval stayed consistent. So 0 to 20,000 has a space of 20,000, and if I look at that same space up here, 180 to 200,000, that same space counts for the same amount. So they have a constant interval, They labeled both of these axes. Their graph is accurate. They even use colors to differentiate things. Great. The one thing I asked for that wasn't here was a title. So that's the one thing that this student left off. Now, of the things they did, I think the title is the least important, which is fine. My thing to the student would be just double check the requirements, or double check the directions that tell you what to put. This student, I'm totally fine with creating electronic graphs like this. This is great. And they have most of the things they need. The main thing that they're missing, like I see we have a label on the x-axis, they have consistent intervals, use color to differentiate things, they have a title here, great. They need a title on the y-axis, title. So that's the problem with this graph over here. And I know electronically you can insert these. This looks like it was done either in Google Sheets or in Excel. You can insert a y-axis title, but I forget where the option is. So just double check the directions and make sure you have all the pieces you need. Good. So those are the main things I wanted to say from yesterday's work. Now I want to move into today, what we're looking at. So I want you to go ahead and pause the video, go back to LMS, open up the activity, and you'll see that this is problem 1 on the activity. So go ahead, pause the video and find the activity now. So I'm assuming you have pulled up the activity, and here we are looking at it. So we've got an insect colony with initial population of 20, and they quadruple every day. So quadruple means multiply by 4. So quadruple, come on, no, that should work. Quadruple is times 4. So if we multiply by 4, you can see 20 times 4 gives us 80. Great. then 80 will multiply by 4 again. 80 times 4 is 320, and then multiply by 4, multiply by 4, multiply by 4. You can do that. So pause the video and do it. Okay, I'm assuming you filled in the rest of these pieces, and now we're talking first differences. Here's what first and second differences mean, and they will be important as we look at other functions. In this case, they'll be a little bit obvious. So differences mean subtraction. And so first differences is if we subtract these two values, then this is going to get messy. But basically, I subtract these two values, and it goes over here. So 80 minus 20 is 60. Then first difference is here. We'll go there. 320 minus 80 is 240. And then find the rest of your first differences. Go ahead. After you're done with that, you can go ahead and find second differences. So 240 minus 60 would be 180 here. And you can fill in your first differences and your second differences. So pause the video and fill those things in. I'm assuming you filled in your population, your first differences, your second differences, and now we're looking at question B. Is the relationship between the insect population here and the number of days here? So this is really just saying we have X value here and Y value here. Is the relationship between X and Y exponential? And explain how you can tell. Well, we've seen back here that exponential is really about this thing that is multiplying constantly. In this case, it was doubling. We saw that here. The important thing is that these things are doubling. We saw that here. The important thing here is that when things double, this graph just blows up and gets crazy because it's doubling every time. So how can you tell that this thing is exponential? Well, we can see the times 4 here. You can see the times 4 here. And you can see the times 4 here. Like first differences and second differences, no matter where we go, the values are multiplying by 4 as we move forward. So that's your explanation here. Go ahead and write it out. I'm assuming now you have finished question 1, and let's go to question 2. So suppose there's a rumor going around in your school and that next year all weekends will be extended to 3 days. What a nice rumor. I would love that. Initially on day zero, we have 5 students that know about the rumor. Suppose that each person who knows the rumor tells 2 more students the day after they hear about it. Assume also that no one hears the rumor more than once. How many people learn about the rumor? So I'll give you the tool that I use in problems like this. I would call this a counting problem. And actually, people in probability, professionals in probability, say that counting is hard, so you know. So good. Initially, we have 5 students. I like to do things like, say, at day 0, we've got 5 students. 1, 2, 3, 4, 5. Great. Then on day 1, each of these 5 students are going to tell 2 people. I do things like this guy tells 2 people, and this guy tells 2 people, and this guy tells 2 people. I think you can already see these 5 people are going to turn into 10 people on day 1, and then we can multiply again on day 2. But I'm just trying to say that this is the strategy I use when I have trouble picturing things. I just go ahead and draw diagrams. So go ahead and finish up question 2. I don't think you'll have troubles. Pause the video, finish it up. I'll meet you on question 3. I'm assuming now you've finished question 2, and here we are with another bacteria colony. So a bacteria colony, oh no, is an insect population in the first one. Bacteria colony has an initial population of 200. The population triples every week. Triples, I think everyone knows, is times 3. So we're going to triple every week. Write an equation to relate the population P to time T in weeks. Well, this is the first time you guys have written an equation. So I'm going to go back here and look. What we know is that this A value up here is the amount that you start at. It's your principal. It's your principal investment or your initial population. It's the amount that we're starting at. And then this amount back here is the amount we're multiplying by. So great. Let's go back and look. So I know we've got y equals a times b to the x. And you know, a is the initial value, b is the rate we're growing at. Well, good, because I can see right here, we have initial population. It literally tells us we're starting at 200. And then it also tells us population triples every week. So those things have to be this b value. So we can go ahead and write that equation. Y equals, we started at 200 times, we multiplied by 3 to the, oh, and I shouldn't use x because they tell us t weeks, which means I also should not have used y. They told us they wanted p population. Y, there we go. P population equals 200 times 3 to the t. So initial value 200, tripling. And to note, we cannot multiply these together to make 600 because the exponent gets evaluated first. So we can't multiply them. It has to stay as 200 times 3 to the t. Determine the approximate population after 10 days. Well, t is in weeks. So 10 days we have to convert into weeks. So 10 days equals 10 over 7 weeks. And that means that that is our t value. So I can go ahead and plug that in. We've got p equals 200 times 3 because we're tripling. And then our time value is 10/7, which is a really weird exponent. I agree. From there, you can go ahead and go to your calculator and evaluate it. Your calculator will know what to do with this. So 3 to the 10/7 power times 200, go ahead and finish it. And then determine the approximate population after 12 weeks. Well, that's easier because t is already in weeks. So go ahead and just take your equation here, input that 12 weeks, go to your calculator again and get a solution. Go for it. Best of luck, and I'll meet you guys on problem 4. Okay, so here's where I really wanted to get today. I wanted to get here today because, sure, yeah, populations grow exponentially, that's true, but your investments grow exponentially too. Any money you ever invest in your life, it all grows exponentially. So we should be able to apply these same functions. So good. An investment of $4,000, I'm starting here. An investment of $4,000 earns interest. This is 4,000, that's our principal. That's what's being invested, which causes it to increase by 6% per year. Great, so we know principal equals $4,000, and we know the rate is 6%, which is the same as 0.06. And it's because we don't want to lose all our money, we want to keep 100% of our money and then continue growing. We have this function y, oh no, they told us a, they told us write an equation for the amount a. So I'll go a equals principal times 100% of our money plus the interest rate to the t power. I don't have an easy way to do to the t power, so I just do this. And they told us to use n. So n, a function of time, n in years. So great, this is what our function looks like, and these are the things we know. We know p is 4,000, we know our rate is 6%, which will go in here. I guess I could color code these things. 4,000 goes in here, 6% goes in here. So our equation then would be a equals 4,000 times 1 plus 6% is 0.06 to the n power. We could simplify that. That's the same as 4,000 times 1.06 to the n power. And this should make a lot of sense to you. When you think about what happens, you are gaining 6%. So in the end, you have 106% of your money. So determine how much the investment is worth after 2 years, 10 years, 20 years. Well, n is already in years, so all you have to do is input those numbers into n and use your calculator. It'll give you solutions. So go ahead, finish those up. And then the final question, what is the value and meaning of the function at n equals 0? So at n equals 0, we would get a is 4,000 times 1.06 to the 0 power. Go ahead and put that in your calculator and evaluate it. I'm sure in your calculator you saw that was equal to 4,000. If you had me last year, you may remember anything to the 0 power is 1. So that whole thing is saying 4,000 times 1, which makes 4,000. So great. What is the value and meaning of the function at n equals 0? Well, n equals 0 is 0 years. If 0 years have passed, we're talking about how much money do you have today. Today you have 4,000. That's what you invested. That's your principal. So that's what we should be left over with. I think you have a solid enough understanding that you'll get through the rest of this activity. So good luck with it. You got this. I will see you guys soon. If you have questions, feel free to reach out.